For today's quiz, we're going to be talking about parallel plate capacitors. This mechanism has a big circular plate and another big circular plate. It's on a rail system. These are metal. This is also going to be metal, but they're isolated through plastic insulators, so I can touch these. If I were to put a meter on here to determine how much capacitance this parallel plate capacitor has, what would happen if I increased the distance? So what would happen to the capacitance of this parallel plate capacitor? Here's what our quiz looks like. I'll hold it up for the camera. As always, mark your answer, draw anything out that you can, put as much as you can onto that piece of paper before we go over it. Let's go over a few student predictions. The first is they think this is a trick question. If the plates don't have any charge on them to begin with, there's no such thing as capacitance. So they think this is a trick question. Others will think, well, the further apart you go, for some reason, maybe it gains more energy and somehow it picks up charge and it will increase the capacitance. Others will say, no, as I take them further apart, I'm going to decrease the capacitance. And others say, well, the capacitance never changes. So let's actually go over this particular experiment. To help us think through this before we actually do our little experiment, again, a parallel plate capacitor is just two plates separated by a distance. Each has some area A. And the formula is as simple as capacitance parallel equals epsilon naught area all over D. Since the epsilon naught doesn't change and the area doesn't change, capacitance is just going to be proportional to the inverse of the distance. So if we ignored each of those, we could say capacitance parallel is proportional to 1 all over the distance. And as D increases, because it's on the bottom, the capacitance would decrease. We should be able to see that over here. I'll go over it one more time as we're doing the experiment. To provide an explanation, let's first of all put this onto our capacitance scale. Some meters have a scale that will measure capacitance. These wires that are connected, or test leads, are for voltage and current. I have two other wires that I've put into the capacitance slot. What I'll do is I'll simply take the two plates together, and then I'll connect each of these using an alligator clip, and then I can use the banana plugs. I'll plug this one into here, and then I'll take the other to the other side and plug it in right here. And right away we can read that it has a certain amount of capacitance. Well, how can that be? Well, clearly there's a battery inside this multimeter. So capacitance can be thought of as the storage capacity, charge per voltage. Now, a parallel plate capacitor also has an equation that says, well, we have some constant of the universe, epsilon naught, but it also depends on the area and the distance. And the distance is on the bottom, so as the distance increases, we expect the capacitance to decrease. And we should see that here. As I pull this away, it certainly does decrease. I was using a string here. I wanted to make sure that I wasn't touching this metal part right here, even though there's an insulator. I normally try to isolate myself as far as possible. So that's our quiz for today.